Hello, I'm Aurora Rossi, and I'm a PhD student at the quality team here at Inria. And today I will present you my recent work about what is happening in our brain while we are listening or watching some narratives. And the content of today will be the introduction to neuroscience. So what is the discipline neuroscience, how to watch inside our brain, the methods to do that, and how to model the brain activity, case in which we study what happened during the narrative. But to do that, I will give you some concept, such as the machine learning concept, like the supervised learning, the division of the brain, and the Shapley value. And then I will show you our model and the result of this Shapley value technique that we applied. And so neuroscience is a field, scientific field in which we study the nervous system of humans. And there are two ways of studying the nervous system. One can be in a structural way, or the other one is the function of the brain. And there are several levels of deep of this study that could be at the highest level, which is the study of the whole brain. But then if we go deeper, we can see, and investigate also smaller structures such as the neurons. And the neuroscience field is an interdisciplinary field, so you need to understand a bit of biology, chemistry, mathematics, and informatics and computer science to understand the brain. And so now I will show you some methods to record the structure or the signal, so the function of the brain. The first one is the electroencephalogram, so the EEG, which is a helmet that you put on your head. It has several electrodes that are recording the brain activity directly, but the resolution, the spatial resolution, so how it can measure the brain activity spatially, is not that high, because we have just 16 electrodes, and it's not well understood also if the signal of an electrode is directly the signal of the area below or can come from another place of the brain. But the good thing of this method is that the temporal resolution is very high, and so it's good when we want to study when something happened in the brain. Another method is the magnetic resonance imaging technique. This method is opposite to the other one, because it has a very good spatial resolution but very bad temporal resolution. And with the MRI, we can not measure the functionality of the brain, but it can show us, so the output of the recording of the MRI is the structure of the brain. And in the picture below, you can see three different levels of spatial resolution. The first one is 3 Tesla, so it's the MRI that usually is done in the hospital. But recently, some French researchers have developed an MRI that can measure with 11.7 Tesla, and so the spatial resolution is way better than the standard 3 Tesla one. with MRI, we can also measure the functionality. And in this case, it's called functional MRI. And it's the same machine, but we measure the function. It's not a directed measurement of the signal because it's called the bold signal, which means blood oxygenation level dependent signal. So it's a measure that takes in account several factors that happen in the brain, such as the level of oxygen in a brain area, the amount of blood flow in the area. And so it's a bit a complex signal to interpret. And so the output of this method is a signal for each brain areas. Now we pass to the modelization of the brain activity, how we can study it in, on the point of view of like computer science or math. Object that can help us to model the brain is the graph. So it's a mathematical structure that can represent some entities, some object, and the relation between them. This kind of structure is composed by two groups, two sets. One are the nodes that represent the object, represent the entities, and one are the link or edges that are the connection between the object. This kind of mathematical structure can model not only the brain activity, but can model, for example, the structure of a molecule, or, for example, a social network. If we consider a social network, the nodes are the people, and the edges are like friendship relations. In our case, we have like the brain activity that is temporal, as a temporal dimension. In this case, the nodes are the brain areas that are always the same. But instead, the relation between these areas change over time. And so we have a temporal network that an example you can see in the picture above, change over, like the edges change over time. Instead, the set of nodes are the same. And this kind of graph is called a temporal graph. Another way to represent the graph instead of the drawing is with a table or a matrix in which like the column and the row represent the nodes, and the element inside the table, which correspond, for example, to row J and column I, is the value or the presence of the relationship between the nodes I and J. And in this case, we have several adjacency matrices because we have more like moments. So it is one for each snapshot of time, so time frame. And so now I will show you in details how from the signal, that is the output of the MRI machine, we can construct this mathematical object, this graph. The output of the fMRI is a signal for each voxel of the brain. So a voxel is a 3D pixel, so you can consider the brain like a set of 3D pixels, and for each of these pixels we have a signal, a recording. And as you can see in the image, we have the a slice of the brain horizontally, and you can see the small pixel, in this case are in 2D because it's just a slice. And so for each of these pixels on the gray matter, which is the out part of the brain, we have like a signal. This signal is a raw signal. So raw means that it contains some noise. This noise is caused by like the patient movement while is in the machine because the patient cannot be completely still, and moreover, there could be the movement caused by for example, the heart rate. And so, the first step to handle this signal is to clean them. And to clean them, we perform a mathematical method that is the linear regression, and we apply also a filter to clean it, which is called bandpass filter, but I will not go into detail of this. And we will obtain a clean signal. And so we will have a lot of signal for each of the voxels of the brain. After this, given the fact that the number of voxels is very high, and we are considering the function of the brain, we want to group, to average all these signals and obtain some signal for each subpart of the brain. We use what is called a brain atlas, which is like a map of the voxel, and that are grouped together according to their functionality. And so then we obtain a signal, that is the average of all the signal of the voxel inside the area. And for example, here we have two clean signal of two bigger areas. And one is the blue areas, and the other is the red area. There are several kinds of atlases. There are atlases that group the voxels according to their structure or according to their functionality. And in this case, we use an atlas that group by functionality. And there are several resolutions of atlases. In this case, we use an atlas with 100 regions. And so we will have 100 of clean signals. And now we are ready to build the graph. And so to do that, we take each pair of brain areas, we take their signal, and we use a sliding window method. So basically, we take just a group of values in the signal, and we compute between the two region we are looking at the Pearson correlation coefficient. So we will have like a value. We will put this value in our table, the adjacency matrix, corresponding to the entries of the blue and red areas. And then the matrix is completed when we perform this operation over all the 100 signals. And then we move a bit the window, and we perform again this computation of the Pearson correlation coefficient. And so we obtain the second adjacency matrix. And we continue in this way until we pass the time dimension of the signal. We obtain a temporal graph that represents the brain activity. Now I will talk about the case in which the recordings come from a patient that is listening to a narrative. I will explain you what we meant for narrative and the dataset we used. So a narrative is a discourse in which there are involved several events and people. And examples of narrative are like written and oral stories, but also movies. And it's important to understand what is happening in the brain while we listen to narrative, because the narrative are the way in which humans exchange information, and then they simulate the reality. And they are rich in variation. They are the opposite of the usual experiments that are very controlled. And in this case that we are also considering the time dimension, narrative have a time dimension. So the dataset we used is a functional MRI dataset of 31 subject participants that were exposed to 16 narratives, and a narrative has a length of 3 minutes. And the narrative could be divided by the modality. So 8 of them were movies, and 8 of them were audio. And then we can also divide them by the content. So 8 of these narratives are related to restaurant situation, and 8 of them are related to airport situation. And so given the fact that we have 888, it's, our dataset is balanced. In particular, what we want to understand from this dataset. So we want to find which subnetworks, so which areas of the brain are the most involved in narrative task. And to do that, we use a machine learning model to classify the modality of the narrative and the content of the narrative. And then we use a technique that is called Shapley values that help us to understand which area of the brain was the most involved in the decision-making process of the model. And if an area is more involved than another one, it means that it's more activated or has something in particular that so is more involved in the processing of the narrative. So now I will give you some concept on what is a machine learning model, how to train a machine learning model, how we divide again the brain in other bigger areas, and the Shapley value technique. As I said before, we had already divided the brain in 100 of regions, but we can group them again using a clustering algorithm and divide them in 7 and 17 regions that have common functionality. And so, for example, now I will describe to you the functionality of the 7 areas. So let's start with the visual subnetwork. It is in the back of your brain, and as the name of the area it processes the information that are concerning objects that are static or they are moving. Then we have the somatomotor subnetwork that control the function related to like motor function and sensory functions. Then we have the dorsal attention subnetwork that it controls the visual spatial attention and integrates the visual and audio stimuli. Then we have the ventral attention subnetwork that detects and integrates the sensory and emotional stimuli. Then we have the limbic subnetwork that is the smallest one and is at the bottom of your head and is related to motivation, emotion, learning, and memory. Then we have the control subnetwork that is involved in problem-solving tasks and decision-making tasks and is on the front of your head. And the last one is the default network, which is involved in the comprehension of history, daydreaming, and thinking about others. Now that I have introduced you like the division of the brain, I want to introduce you the concept of supervised learning. So, as I said before, we used a machine learning model to classify the content and the modality of the narrative. And to give you like a description on how we did it, I want to first introduce like the supervised learning technique. So when you have a machine learning model, there are several ways to update him. And in this case, with the supervised learning, there is a data set that is used to train the model. And so you give some input to the model output a value, and then you compare the value of the model with the real value you expect from the model, and then you update it in order that the model, when learn to predict some output given new input. And so the training can be considered as an optimization problem in which the output of the model has to minimize a certain function that is called loss function. And here there are two basic loss functions. One is the mean absolute error, and one is the mean square error. And so the loss function takes as input two values. One is the real value that we want that the model output, and one is the model output. And so then we compare the two by taking the difference. And in the first case, we take the absolute value. And in the second case, we take the square of the difference. As I said before, to train a model, we need a data set. And the data set is divided in two sets. One is called training set. So it's the set that the model uses to learn. And so the model sees the input and the output. And instead, the test set is the set to see the performance of the model on new input. And when we say that we train the model, we mean that we update its weights. So the model can be updated, and every time that when you see a new input and output, we update the weight using the gradient descent algorithm. And so basically the weights at the iteration i+1 takes the weight that he had before, and then he subtracts the gradient of the loss function multiplied by a learning step. And now I told you how to train a model, but I will also introduce you some basic model. So these two are like the most basic one. The one on the left is the dense layer. So this layer is inspired by the neurons of the brain. And basically it takes an input that is a vector and is x, and is multiplied by the weight, some weights that are these lines, so these links. And then is passed in an activation function that the most famous one is the ReLU, that takes the maximum between 0 and the output of the multiplication. The concatenation of these layers together, it's called a multi-layer perceptron. In fact, on the right, we can see that there are 3 dense layers that are concatenated. And every time the dimension of the input is decreased. Another basic machine learning layer or neural network is the convolutional neural network. The convolutional neural network was created to classify images. For example, we give to a convolutional neural network a picture of the cat, and the output will be cat. And so it has to classify, for example, between cat and dog. And how the convolutional neural network does this? So we can consider the input as an image or a table of number matrix. And in fact, because the images can be translated in matrices. And then we, as before, we have some weights that can be updated. And in this case, the weights are contained in the filter. In this case, I put a fixed one. And the filter has to be superposed to the image. And then it is, like in the picture, shift every time. And every time that is superposed, it computes the, it's called element-wise matrix multiplication. So if we see in the first 4 elements, is superposed the filter, and so we take just the 2 elements on the diagonal, and then we sum them together. So it's basically 1 plus 5, and output 6. And then this process is repeated every time that we shift the filter. And so the filter basically aggregate the information around the point where it's superposed, reducing it. And in the picture below, you can see several layers, so several repeated convolution from the input to the output. And the output is a vector that say to you like if it's a cat or a dog. Now I will talk about to the last concept that are the Shapley value. The Shapley value were introduced in the context of game theory, and they quantify the contribution of some players in a game. And the game we are considering is a coalition game. So the game in which the players work together to reach a common goal. And so the contribution of one player in a set of players n is given by this formula. And so it's the sum of over all the subset in the set of the player. And there is a multiplication between a factor and the payoff of the set with the player we are considering and without it. This can look complicated, but now I have a simple example to show you how it works. So we can consider a soccer team. So a soccer team should collaborate, work together to reach the common goal of like put the ball in the net. And so in this case, we have just 3 players that are in the same team. And if we want to understand the contribution of the first player, so the one on the left, what we have to do? We have to consider all the subset with him and without him. So let's start with the first subset, that is the empty subset. And then we consider this set plus our player, and so which is this one. And then the formula say that we have to subtract to the set in which there is the player. The payoff of the first player is 2 goals in this case, and minus 0 goals in the case there's nobody. And then we repeat this thing, so we consider another set, so the set in which there is the player 2, and again this set plus the first player. And then again we subtract the second one with the first one. And then again, so we have the third player and the third player and the first player, and then we do 3 minus 1. And again, the set in which there are all the 3 players minus the second and the third player. And in this case, with this computation, we obtain the Shapley value of the player 1. And then it's repeated also for player 2 and 3. Okay, so now we go on, and we will, after I introduce you this concept, you should understand better the model and how the Shapley value play a role in understanding which brain area is the most important one. And so, again, what we want to understand is which sub-areas, which sub-network in the brain are the most important, most involved in a narrative task. And so we use a machine learning model, and with the Shapley value, we compute the importance of the sub-areas. And so, in this way, we can comprehend better what is happening in the brain while we are watching or listening to narratives. So, with the machine learning model, we first classify the modality. So, given as input the temporal graph, the model performs some computation, and the output will be movie or audio. Then, same thing, but with the content. So the model will tell us if the patient was listening to a narrative about an airport or a restaurant situation. And then also the combined classification, which means that the model can tell us, okay, the patient was watching a movie about a restaurant situation. So the model is very simple. So the input is the temporal graph. Then it is applied a convolutional neural network. In this case, is a 3D convolutional neural network. Before I show you the two-dimension one, because we had just a picture. In this case, we have it's like that we have a series of pictures, so we can consider it as a 3D object. And then we apply a multi-layer perceptron, that is a concatenation of some dense layer, that will output the answer. So another way to see the 3D convolution, so this is the temporal graph show you in embedded in the planar space, and the filter in this case is large as the wall adjacency matrix and has two dimensions across time. And again, the filter shift just across the time dimension, and every time that is superposed to two of the adjacency matrix, it's compute the component-wise multiplication, and so the result is just a number for each shift. And then all the numbers below are the input of the multilayer perceptron. And so this is a vector that will be multiplied, then passed to a activation function for like 3 steps. And then we will have the output. So now we look into the results. So this is the classical way to show some machine learning result, like the performance of the model. There are several metrics, but the one that we care about in this moment are the accuracy. So the accuracy reflects the number of correct guesses of the model. And which means that if we give to our model, for example, 10 inputs, and the model guess correctly just 8 of them, then the accuracy would be 80%. In this case, when we classify the modality, so we classify between movie and audio. The accuracy, as you can see, is very high, is 96%. And so this means that it is easy to classify between movie and story. Then instead for the content, the accuracy is still very high, given the fact that it's less intuitive to understand the difference between the context of a story. And the combined classification has the same score of the content one. And in the last row, instead, there is the accuracy when we permute the time. What does it mean? You saw that we have the adjacency matrix of the temporal graph, and it has a certain order. So we shuffle this order, and also we are destroying the temporal pattern. And for the classification of the modality, this is not so affected as the content, because you can see the modality is a drop of 10%, and instead the content is almost 20%. And this is quite intuitive, because to understand the content of the narrative, it's important to follow the time dimension. So how we use the Shipley value in this case? As I said before, the Shipley value compute the contribution of a player in a collaborative game. And in this case, our players are the brain areas. And we mask, to highlight just the player we want, we mask the other by setting to 0 the entry of the adjacency matrix. And so in this way we can compute the contribution of just some areas. And here there are the results. In this plot we have the result for the 7 areas and 17 areas, and are the result for the modality classification. So when we try to classify, to distinguish between movie and audio. And as expected, we see that the visual area is the one that has the highest Shipley value, and is intuitive, because in one case the patient has just to listen to a story, and in the other case he has to listen and watch the movie. Then we have the result for the content classification, so the comparison between restaurant situation and airport situation. And in this case, is the most involved area is the default network area that has a very high Shipley value compared to the other areas. We saw before in the list of the function of the networks that this was responsible for story comprehension, and in fact it appears as the most important one. And also in some other works by Baldassano and Simoni, was suggested that this area would play a role in the comprehension of stories. And then to understand the next result, we have to introduce 2 kinds of processing of the information. So when we receive a new stimuli, there are 2 ways of process it. So the first one is the top-down process. So when we receive a new stimuli, it means that we use our previous knowledge to elaborate it. And this is associated with the dorsal attention subnetwork. And then there is the opposite way of process. So it's called a bottom-up process, in which when we receive a new stimuli, we don't use the prior knowledge that we have. And this is associated with the ventral attention subnetwork. And so in the result of the content classification, we can answer to an open question, which is that the narrative, the process of the narrative, is not just like a top-down process, but it is a combination of the two processing. There is also a bottom-up component, and this question was raised by the paper of Baldassano. And with our result, we can step forward to answer to this question, because, as I said before, the bottom-up was associated with the ventral attention, and we see that in the 17 areas, the ventral attention B area has a high Shapley value. And then we have the combined classification result, and as expected, both visual and default areas are the most important one, but also also the somatomotor A area has a high Shapley value, because can be understood in the embodied cognition field, which means that when we read about an action, even if we don't perform the action, in our brain, in the part of the brain that is related with the motor activity, the brain activity is a bit increased, even if we don't perform some motions. Thank you very much for your attention. Here there is a QR code of my webpage. If you have a question, there is also my email, and there is also the paper about this work. Okay, and of course there should be time for questions now.
Est-ce qu'on peut imaginer qu'on enregistre ce qu'on rêve? Mais comment, what you dream of?
Yes, but we have to scan while you are dreaming. Yeah, but yes, we can. And this combination of technique is power. Like in this case, we already know some result, so it was a bit of validation of the process, like of the technique. But this technique can be applied in the case in which we are not sure which brain areas are involved in some task. Yeah. So also in dreaming, maybe we don't, like if we perform this analysis, we can see that maybe a brain area that we don't know that is particularly activated. So we can discover which one are more activated. Yeah.
Merci Aurora. Cette question ou d'autres commentaires? Des questions? Anne me fait signe de questions par là. Le micro est pas super long, je parle français.
Par rapport au rêve, vous avez dit que techniquement ça pourrait être fait, mais ça n'a jamais été réalisé.
Because it's a bit difficult to scan the person while he's dreaming and while he's sleeping. Yeah, because it's difficult to find a data set for MRIs, because it's very expensive to do them, and so there are few of them. It's instead for the EEG, it's way cheaper. There are a lot of.
Bon, on a peut-être un tout petit peu de temps. Peut-être Aurora, c'est bien que tu dises un mot sur ton parcours, aussi comment tu es arrivé là, parce que tu viens d'un pays qui très loin. Mais c'est intéressant de voir un peu quel est ton cursus avant d'arriver pour faire une thèse.
Okay, prepared a slide for that. So I did the bachelor and master degree in Italy at the University of Verona. And in particular, the bachelor was in applied mathematics to economics. And then the master was just general applied mathematics. Then during the master, I was the tutor of several courses, such as the operation research course and linear algebra course. And in the math degree, there was not a lot of courses about coding and programming, but with the experience of tutoring, I developed the coding skill. And then while I was in the master, my professor would encourage the student to go abroad with the program that is called Erasmus. I did an Erasmus Plus, which is an Erasmus in which you don't do exam, but you just go abroad for an internship. And so my professor suggests me an internship at Inria. And the internship was graph theory applied to neuroscience, so similar to this topic. And then I graduated and I stayed here for the PhD. And so now I'm the last year of PhD. My PhD is about machine learning, graph theory, and in particular the part of temporal graph. And I did some application to neuroscience. And during the PhD, I also participated to Summer of Codes. So during the summer, you contribute to open software. And one was with Google, and one with Julia, which is a recent programming language. And so during my PhD, I did a lot of research, but also a lot of coding and contribution to the open source software.
Ça, je vais peut-être faire aussi. Ok. En tout cas, on remercie à nouveau